So this effect of respiration and photosynthesis on carbon dioxide and then on the pH of the ocean, we can actually measure this. So this is a generalized graph showing what we actually measure in the ocean over time, where during the night, you have more respiration, so the pH starts going lower, right? So lower pH is more acidic. pH goes down. Then, once it's daytime, now you're getting photosynthesis. The carbon dioxide's getting consumed, so less carbon dioxide. So the pH starts going up, and you have a higher pH, less acidic conditions. And then during the dark, again, no photosynthesis, just respiration, more carbon dioxide, pH goes down. Then during the day, you have photosynthesis, less carbon dioxide, less acidic, so pH goes up. And so you can actually measure this in the water over time based on the changes in photosynthesis and respiration. And the last thing I wanted to talk about with carbon is the biological pump, because this is a very important flux of carbon in the ocean. So again, carbon dioxide comes from the atmosphere, dissolves into the ocean, and most of the carbon dioxide that is produced, for example, through burning of fossil fuels, actually does end up going into the ocean. Because as soon as it gets in the water, it's largely consumed by phytoplankton. Again, they're doing photosynthesis, they're sucking up the carbon dioxide. Then those phytoplankton are getting eaten by other organisms, things like zooplankton, and zooplankton get eaten by fish, and that fish gets eaten by a bigger fish, etc. So it's getting put through the food chain, the food web, which we'll talk about later. And it is then getting pushed into the deep sea by things like dead bodies. So, like if the fish dies and sinks into the deep ocean. Also, fecal pellets, so like little poop, uh, like nuggets, basically. Sounds terrible. Little poop pieces that come mostly from things like zooplankton, copepods, rain down from the surface. And this actually pushes carbon into the deep sea a lot faster than if it was just like dissolving as a gas through the water. So this causes a larger flux of carbon into the deep sea, where it is much less likely to get back into the atmosphere very quickly. Whereas if it's staying in the surface, like as a dissolved gas, it's much more likely to kind of flux back and forth from the atmosphere to the ocean. So when you're making climate models, again, trying to predict how carbon dioxide is going to increase in the atmosphere and how that'll affect temperature, accounting for this biological pump is actually a really important part of figuring out how quickly carbon dioxide levels go up. So a lot of carbon dioxide is getting pulled out of the atmosphere and kind of pushed into the deep sea by this process. So that is the biological pump. Next up, we're going to talk about the nitrogen cycle. Nitrogen is important because it's an essential nutrient for both plant growth and animal growth and algal growth. Most of the nitrogen in the ocean gets there. Well, it gets there in a couple ways. First, it can get there through organics coming in through rivers, but also a lot of it dissolves, similar to carbon dioxide, dissolves from the atmosphere into the water as nitrogen gas. Uh, However, when it's in the form of nitrogen gas, most organisms can't use that. So, like things like most phytoplankton can't use nitrogen gas to like get their nitrogen, which again is a nutrient that they need. So, if we have nitrogen gas, but as all living organisms are like, hey, we need that nitrogen. What do? They often rely on nitrogen fixation. So there are certain bacteria, primarily cyanobacteria, that are special, and they're able to do this process called nitrogen fixation. They convert nitrogen gas into other forms of nitrogen, things like nitrite, nitrate, ammonia, that can be used by other organisms. So it's converted the nitrogen into this form that things like other phytoplankton can use. So now they're able to use it as a nutrient, get that nutrient they need. So this can be really, really, really important process, especially in areas where that are like not near land, where they're not getting other forms of nitrogen from places like rivers, right? Because if you're like in the middle of the Pacific Ocean, there's not any rivers near there, so you're not going to be able to get your nitrogen from rivers. And so instead, a lot of the open ocean relies really heavily on nitrogen fixation. To turn nitrogen gas into the like nutritious forms of nitrogen that phytoplankton and then anything else higher up in the food chain can actually use. So, very important process in the oceans and on land as well. Next up, the phosphorus cycle. Now, typically there are not phosphorus gases. Most phosphorus exists in the form of phosphate, which is like an ion. And most phosphorus in the form of phosphate comes into the ocean through rivers. So again, similar to nitrogen, but you get a little tiny bit coming in through the atmosphere, but the vast majority is coming from rivers. And that gets in the rivers through things like eroding of land rocks, and again, organic forms as well. But that is another very important nutrient for things like primary producers and consumers going all the way up. Next up, we're going to look at how we delineate the ocean environment, ecosystems. We already talked about this a little bit, so there may be some overlap with previous lectures, but we're going to talk about, again, how we split up the ocean into zones. So, for example, you have the intertidal, also sometimes called the littoral zone. This is the little horizontal section of beach, often, that is covered and uncovered by the tide. So, at high tide, it's underwater. At low tide, it's out of the water. That is the intertidal area. Then, if you were to keep going out to sea, you have the neritic zone. This is the area of water that is over the continental shelf. So remember the continental shelf, when we talked about geology, it sticks out from the land before dropping off into the deep sea. So again, it's that relatively shallow area right next to land. And most of ocean life is located right here on the continental shelf. Then the oceanic zone is when you are now over the deep, deep, deep ocean. So it's the horizontal portion of the ocean that is off of the continental shelf and above like the abyssal plain, all that really deep ocean. Next question for today is, why do you think it is that most ocean life is found in the neritic zone on the continental shelf? So most of the space on Earth is actually deep sea. It's that oceanic zone. But even so, most ocean life is found on the neritic zone, which is that little like fringe of continental shelf at the edge of oceans. So why do you think it is that there's so much more life in that area?